Hello everyone, welcome to section 5.2. This is mathematical induction. So first, what is mathematical induction at all? Well, this is going to be a proof, a style that is completely different from direct proof, from contraposition, from contradiction. In general, it is a method that is used for proving that a property defined for integers is true for all values of n after a certain point. Instead of checking infinitely many cases like we will have to do, then what we do is we prove that the property holds for the first case, which is going to be called the basic step. And if that's true, then we check that is true for the case of k. And then we prove that for the next one, it's also going to be true, which is what we call the inductive step. This creates some sort of chain reaction that proves the property for all cases. So you can imagine this like a collection of dominoes that its positions have. So if one domino falls, the one behind is going to fall too. So if the first domino falls, what happened? They all going to fall down. Why? Because the first domino falls, and then that's going to go to the next. So the first domino here is the basic step, the property in the first number. And each domino that knocks over is just proving the inductive step, which is if P of k holds, then P of k plus 1 holds. And at the end, all the dominoes are going to fall. So the conclusion is that the property is true for all the n bigger than 1. So the principle of mathematical induction is defined precisely as follows. Let's assume that we have P of n be a property defined for integers n, and let a be a fixed integer. Now, the basic step is we're going to prove that the property is true for that particular number. Notice that it doesn't have to be 1, it doesn't have to be 0, it can be any particular number, but we gotta pick it and choose it, and we gotta show that for the first basic step, that's gonna be true. The property is gonna be true for that number. Then after that, we're going to assume for any integer that is bigger than that initial number, if the property is true for k, then it gotta be true for k plus 1. That's our inductive step. So this is what we have to prove. We got to assume that P of k is true, and then prove that thanks to that, the next one, P of k plus 1, is going to be true. That's what we call the inductive step. Then the conclusion is going to be, oh, okay, so if that happens for all n bigger than a, P of n is going to be true. Now, in other words, you can prove these two things. You prove P of n for all n bigger than a. Now, in general, the method of proof by induction goes from the basic step that verifies the property at the starting point. Then it goes to the induction step that proves that for all integers bigger than that initial point, if P of k is true, then P of k plus 1 is going to be true. And then in here, we have our inductive hypothesis, which is the P of k, and you're assuming here that P of k is true, and the goal is to show that P of k plus 1 is true. And then finally, you get to the conclusion that by the principle of mathematical induction, P of n is true for all n bigger than a. So this is going to be your structure to prove anything by induction. If you're going to prove anything by induction, you need to have every single one of these steps on your proof. So this is going to be part of the final project. So it's very important that you understand each of the pieces of the proof by induction so you can do it yourself carefully. So remember, you're going to have all the step outlined, the step 1, the step 2, and the conclusion. All this, you got to go over all these steps. But now let's check a complete example of this so it's more clear. So we're going to have that for all integers bigger than 1, you're going to have that the sum of the first n integers is n times n plus 1 over 2. Okay, so pretty much this sum of the first n integers can be simplified to just multiplying n by n plus 1 divided by 2. So it's very nice to have this property because it's a very complex sum and can be a very large number, like a million. And then you simplify that sum to, oh, I just multiply the number by the next one and divide by 2. And that's it. Now, let's prove this by mathematical induction. First, this is the property. So what we want to prove is the property. We define it, P of n is the sum from 1 to n is equals to n times n plus 1 over 2. Now, the first step is to show that P of 1 is true. Why P of 1? Because we're going for n bigger or equal than 1. So we need to prove it for 1. So, okay, so let's verify the formula when n is equals 1. So when n is equals 1, the left side is just going to be 1. Remember, what is the formula? This. So the left side is just the sum from 1 to 1, since n is equals 1. So on left side is 1. Now on the right side, we have 1 times 1 plus 1, and then everything divided by 2. But notice this is 1 by 2 divided by 2, so it's 2 divided by 2. It gives me 1. So now we can see that the left side is equals to the right side of the equality. And so since both sides are equals to 1, P of 1 is true. Now the step number 2 is going to be the inductive step. So we're going to prove that for all k bigger than 1, if P of k is true, then P of k plus 1 is true. So first, we need to state the inductive hypothesis, which is, let's suppose that P of k is true for some arbitrary k bigger than 1. What does that mean? That means that the sum from 1 up to k is going to be k times k plus 1 over 2. Notice that we're assuming that this is true, so we're going to use it. That's going to be the next step. We're going to use it because we are assuming that this is true. So this is an hypothesis that we're using. Now, when we reach this point, then we want to prove that P of k plus 1 is true. But what is the shape of P of k plus 1? Notice that now is going to be the sum up to k plus 1. And we want to prove what will be that in terms of k plus 1. The other side will be where I had k before. Now I'm going to replace by k plus 1. And so I get k plus 1 times k plus 2 divided by 2. I want to prove that. It's not proven yet. So because I want to prove it, I'm going to start from one side and I want to reach the other side. Okay? So let's start with the left side of P of k plus 1. So that's left side is just going to be the sum up to k plus 1. But here is where I can group. Why? I'm going to group the first k terms plus k plus 1. Why? Because I have information about the sum of the first k terms. The hypothesis of induction tells me that the sum of the first k terms is actually k times k plus 1 over 2. So I can simplify this entire sum and just put here k times k plus 1 over 2 plus k plus 1. And so now at that point, I need to do a little bit of algebra manipulation here. I'm going to factor out k plus 1. And so notice that if I factor k plus 1, I get k over 2 plus 1. And so now if I simplify this, if I put this in a single fraction, that's going to be k plus 2 divided by 2, right? 1 can be seen as 2 over 2, so put this together in a single fraction, and I have that. And now, notice that because the multiplication is associative, I can see this as k plus 1 times k plus 2 over 2, which is exactly the right side of P of k plus 1. So with this, I've proven the inductive step. So far we've shown P of 1 is true, and we show that if P of k was true, then P of k plus 1 was true. Then, for conclusion, we say, okay, therefore, by the principle of mathematical induction, then the sum from 1 to n is going to be n times n plus 1 over 2 for all integers bigger than 1. Let's do another example. So for this one, we're going to prove that if we have the sum from I equals 0 to n of r power to the I for any r that is different from 1 in any integer n bigger than 0, then this is just going to be r to the n plus 1 minus 1 over r minus 1. Notice that I'm writing here the property in terms of the sum notation, but I can just write what that is, which is the sum from r power to the 0 to r power to the n. So now, what really my property is P of n is that the sum from I equals 0 to n of r power to the I is just r to the n plus 1 minus 1 over r minus 1. So now, the basic step, let's show that P of 0 is true, since we're starting from 0 here. Now, the left side is the sum from 0 to 0 of r to the I. That's pretty much just r to the 0, which is going to be 1. Now, the right side is, well, what is r to the 0 plus 1 minus 1? Oh, that's going to be r minus 1 over r minus 1. That's also 1. And so since both are equal, we know that the first condition, the basic condition P of 0, is going to be true, and we have the basic step. Now, let's go to the inductive hypothesis. Let's suppose that P of k is true for a k bigger or equal than 0. So the certain k. So that means that the sum from I equals 0 to k of r power to the I is going to be r to the k plus 1 minus 1 divided by r minus 1. What's our goal? Our goal is to show P of k plus 1. And so we want to prove that from I equals 0 to k plus 1 of r to the I, that's going to be r to the k plus 2 minus 1 divided by r minus 1. Notice that this is just like we're replacing here where we have k by k plus 1 and we have a new formula. But that's what we want to prove. We want to prove that the formula keeps working out. It's always the same regardless of the n that I'm using. So now, for the proof, I start with one of the sides, of course, that's what I need to do. And I'm going to use the induction hypothesis. So I'm going to write the sum from 0 to k plus 1 of r to the I as the sum up to k plus the term k plus 1. So I will have what I have, the sum up to k, which I can later, by the hypothesis induction, see as r to the k plus 1 minus 1 over r minus 1, because this is my hypothesis. I have this plus the term r to the k plus 1. So now when I have this here, what I want to do is I want to simplify this into a single fraction. So because this has an r minus 1, what I'm going to do is I'm going to multiply by r minus 1 top and bottom. And so at that point, I can make this into a single fraction since they both have denominator r minus 1. I multiply this here and I get r to the k plus 2 minus r to the k plus 1. And so notice that I have this term and this term that they can cancel each other. And now I'm going to get r to the k plus 2 minus 1 over r minus 1. So I pretty much arrived to the left side. From the left side of the pk plus 1 condition, I'm arriving to the right side. And so I just prove that the pk condition implies the p of k plus 1 condition. So now here, by induction, then I will be proving that this works for any n. And that is the end of the proof. So now some key points here. You gotta remember the structure of the induction proof. Once again, this is very important because you need to have this in every proof. You need to do the setup. You need to state what's the property that you're proving and identify the initial value that you're gonna use. Then you need to prove the basic step, which is verifying that the properties hold for that initial value. Then the induction step, first, you need to state what is the inductive hypothesis. You need to assume that P of k is true, and then you have the goal of proving that P of k plus 1 is true. Usually it's good that you state it as well, so you have your goal clear, and then you start from either one side of the assumption of pk plus 1, and then you arrive to the other one. Or in general, what you do is you prove P of k plus 1 by a manipulation of the conditions of P of k. And then last, the conclusion is that by mathematical induction, then that's going to be true for all natural numbers after the initial step, after the initial number. You need to avoid certain common mistakes here, which is forgetting using the basic steps, or not stating the inductive hypotheses, or assuming what you want to prove, which is always a mistake, or not using the inductive hypothesis. You need to use the inductive hypothesis to go from assuming that P of k is true and proving P of k plus 1. Okay? You also got to be careful not starting with the wrong value. If your statement starts at 0, at n equals 1 or other, you need to use that for your first step. Okay, so in summary, we just introduced the mathematical induction process, the two steps that are initially required for it, the basics and the inductive. We just discussed how the inductive hypothesis is proven, where you assume that P of k is true, and then you prove P of k plus 1. And the strategy that is usually in the inductive step, where you start with P of k plus 1, separate the k plus 1 term from the k, and then use hypothesis on the first k terms to manipulate and to reach the form that you desire. Okay, so for our next video, our next section, we're going to go on induction for divisibility and inequalities, but make sure to check the examples for this section, since I'm going to be doing much more cases of induction. They're hopefully going to help you understand this better.